Hi. So, now we've got only one more case of integrals to cover. This case is associated with improper intervals. So, this is a very special type of integrals, and we generally can encounter improper integrals in two cases. The case number one is when we have infinite limits of integration. Okay, so what does it mean? Look, for example, what if we have an integral from a to infinity f of x dx? Then we would get f of infinity minus f of a. How much is that? We don't know. We don't know whether this is infinity. We do not know exact number what it is. So basically it leaves us a very problematic situation. We simply cannot evaluate the value of this expression. But look, of course we can have a case where we have an integral from negative infinity to some b. And again, we are encountering the same problem. And finally, we can have a situation when we have an integral from negative infinity to infinity. This one you're going to do in statistics. Very important case. And then we have f of infinity minus f of infinity. And look, all these three cases are simply impossible to evaluate. We just cannot calculate the exact values of these expressions. Well, we can do it using the techniques we've been using thus far. But look, our experience should tell us that if we have a situation like that, then we have infinity somewhere, what we can resort to? Limits, of course. So look, in the first case, we can say that this integral, so from a to infinity f of x dx, is by definition given as a limit with b approaching infinity out of ab f of x dx. And look, similarly, in the second case, integral from negative infinity to some b f of x dx is by definition given as a limit with a approaching negative infinity out of a b f of x dx. And finally, if we are in case number 3, so we need to evaluate, we need to calculate this improper integral. Then we need to calculate two limits, basically. So limit with a approaching negative infinity and b approaching infinity out of, again, the same expression. Now, if limit exists, because remember, limit does not always have to exist. And of course, we're going to actually, when we're going to move on to example, I'm going to cover with you a case where the And we say that that improper integral is convergent or if it's not, so otherwise it is divergent. Okay, so now the new trick, how to calculate those integrals. Let's start with an example. Okay, so look, let's just say that we have reciprocal function 1 over x. And let's just say we are interested in what is the area below this function from 1 to infinity. So I want to know what is the size of this entire area from 1, but of course till infinity. Okay, so look, we already know how to approach this problem, so let's start. Look, this means that we need to calculate integral from 1 to infinity out of 1 over x dx. So we are calculating integral from 1 to infinity out of x to the power, x to the power negative 1 dx. Okay, look, now we need to, of course, use the logarithmic rule. But again, because we've got it from 1 to infinity, it's positive. We don't need to use natural absolute value. So we got that this is a natural logarithm of x, and here we've got b approaching infinity 1. Okay, and look, now how do we approach it further? First, we substitute b. So first expression here is going to be limit with b approaching infinity out of ln b. Then minus ln 1. As it's, of course, ln 1 is just 0. So this part is inconsequent. Now, over here, how does ln x function look like? Ln x function look like this. It goes through 1, and it increases indefinitely as x is increasing, right? So the bigger the b, the bigger the ln b. So in this case, limit is equal to infinity. So limit does not exist. So in this case, area cannot be calculated. Okay, so now let's change the situation a little bit, our function, and let's introduce, instead of instead of y equals to 1 over x, let's try the function y equals 1 over x squared. Okay, so this function looks very similarly to this one, but of course, first, both sides here are above, both parts of the function are above the x-axis, and remember, this is x squared, which means that here, when we were dividing here by 1, we got 1. Then when we were dividing by, when x was 2, we had 1 over 2. Then 1 over 3, 1 over 4, 1 over 6, right? Here, values of the function actually are dropping a little bit faster. Because, look, if x is 2, we've got 1 over 4. Then we've got 1 over 9, 1 over 16, 1 over 25. So you see, the values of this function are declining faster. Now, let's see whether this is going to have any impact on our results. Because we still want to know what is the size of the area below this function between 1 and infinity. So from 1 to infinity. So again, we need to calculate integral from 1 to infinity out of 1 over x squared dx. So we get that this is integral from 1 to infinity out of x to the power negative 2 dx, which is equal to integral. Of course, which is equal to x to the power negative 1 divided by negative 1, right? So minus negative x to the power of negative 1. Okay, and here we've got b approaching infinity and 1. Okay, so look, we go through exactly the same steps, right? So we calculate limit with b approaching infinity out of negative b to the power negative 1. And minus negative 1 to the power negative 1, right? Okay, let's rewrite this a little bit before we start calculations. Look, here we've got that this is limit with b approaching infinity out of negative 1 over b, right? But out of this, we're going to just get plus 1. Okay, so now let's think, what is the value of this expression? Look, if we divide 1 by b, and b is getting bigger and bigger and bigger, right? The expression gets smaller and smaller and smaller. So as b is infinitely big, so as we divide by infinity, this expression goes to 0. So look, our limit, our improper integral is equal to 1, because this turns into 0. So look, this time it turned out that size of this area is 1. And now the question would be, how is that possible? How is that possible that this, that we okay, look, when you think of areas, the good thing to use to think about areas is to think of them in terms of some rectangulars, right? The rectangulars are easy to imagine, and we know that in order to calculate the size of the rectangular, all I need to do is to multiply A by B. Okay, and look, we know that the distance over here and over there is 1, right? So look, if we would have a rectangular, hypothetical rectangle with one side equal to 1 and the other side equal to infinity, then 1 times infinity, it's definitely infinity. So it would be indefinitely big. But look, we know that the values of the function here are dropping, right? So they're getting smaller and smaller and smaller. So look, we actually definitely not going to have infinitely big area. We're going to have area that is smaller than infinity. Well, but it's still... sorry. Okay. It's getting closer and closer and closer over here. Right? And basically, from this point on, it's still declining, but we barely see it. Right? Because we do not have microscopes in our eyes. Okay, so, look, what is the idea behind this? Like, we know that this area is definitely lower than infinity, unlike over there, but why is it so small? How is it possible? How is it possible that something that is going for so long is actually an area that is so tiny? And look, and why in this first case? Okay, let's just say that from now on, this red, pink, orange color is associated with the function 1 over x squared, and the blue color is associated with the function 1 over x. Look, if I would like to draw a similar picture for 1 over x squared, it would look more or less like this. Okay, so we clearly see that the values of the function 1 over x are falling, but they are falling slower than the values of the function 1 over x squared. And look, this is the entire key to understanding what is happening. Look, in the first case, what we see, one side is getting longer and longer and longer. One side of the rectangle, right? But the height is getting smaller and smaller and smaller and smaller and smaller. Now, the question is, can the fall in what is actually having stronger force? Increase in the length or the fall in the height? And look, the answers we already have on a blackboard. Look, in case of 1 over x, you can imagine it like this. The fall in the values, in the height, is too slow to compensate for the increase in the length of the increase of the length, right? However, in case of this function, the reverse is true. Look, here actually values of the function, so the height is dropping actually faster than length is increasing. So it cannot so each increase in length is more than compensated by decrease in height. This is why in cases of some functions like 1 over x, we cannot calculate the area because it's too big. So it's infinitely big because the fall in height is not compensating for the increase in length. However, in other functions, like in case of function 1 over x squared, the opposite is true. The fall in height is faster than increase in length. And this actually can create such a paradoxal to, when you first hear it, result that this entire area is equal to 1, especially that just a couple minutes before calculating that this is equal to 1, we've calculated that this is infinitely big, right? And they look almost the same. However, once you understand the difference between the two, you see where those two outcomes are coming from. Okay, look, the case of infinite limits of integration is the more important case. But, of course, we need to consider the second case in which improper integrals are arising. And this is the case of infinite integrand. Okay, and let me just illustrate the case of an infinite integrand with a very simple example. Again, resorting to the function y equals 1 over x. Okay, so let's just say that now I want to know what is the size of the area below this function between 0 and 1. So I want to know what is the size of this. Okay, now the thing would be to calculate an integral from definite integral from 0 to 1, right? And out of 1 over x dx. At the beginning, it doesn't seem like a problem, but it is a problem. Why? Well, we cannot substitute 0 in function 1 over x. But then, we still haven't integrated this function. Oh, but this problem is not resolved once we do. Because look, if I integrate this in between 0 and 1, I don't need to use absolute value, but I'm getting ln x. And then 1 and 0. And look, again, I cannot substitute 0 instead of natural logarithm of x. This expression is not defined. So again, I need to resort to limits. Okay, so what am I doing over here? First, I can just substitute 1. But then, I need to subtract a limit with a approaching 0 from, of course, the right hand side. Let me just put it in here. Out of ln a. Okay, because this one, sorry, ln1 is just 0. So we will have that this is equal to negative limit with a approaching 0 from the right hand side out of ln a. Again, let's see how natural logarithm of x looks like. Okay, and look, what do we see on this graph? As x is getting closer and closer and closer to 0, what is happening to y? Y, so ln x is getting lower and lower and lower and lower. Where does it go? To negative infinity. So what we get over here is minus negative infinity, which gives us infinity. And again, we have a situation in which area cannot be calculated. Okay, so this is it. This is everything you need to know about mathematics for my exam. I'm gonna prepare just one more video, and in this video, I'm gonna tell you how your exam is going to look like. Well, it's gonna be online, but okay. This is it for today. Thank you for your attention and good luck on the exam. Take care.